Hi everyone, Elliot Jacobson here for Advanced Advantage Play. And today I want to talk about a topic that I'm surprised I've never covered before, and it comes by way of an email. The email reads, "Hi Dr. Jacobson, I'm wondering if you could help me understand the thought process and mechanics behind finding vulnerable bets, analyzing and attacking them. How would one go about identifying which side bets could potentially be vulnerable to counting, and then confirming the suspicion and creating a counting method for attacking it?" So this question is great, but I just have to tell you in advance, it is a bit complicated to answer. And I'm actually going to give you an example and go through the entire process start to finish. So this video might not be for you, but if it is for you, I hope that I answer every question you have somewhere along the way. Well, the first thing we need is some brand new side bet I have not yet analyzed, so that this is worthwhile for me. And fortunately, I got an email just recently with a side bet that I have not yet analyzed. And if you look down this email, "Dear Professor Jacobson, I was wondering if you could do a similar simulation for one of the tiger bets." And the one I want to focus on, if you read right down there at the bottom, is this tiger bet that pays 23 to 1 when the banker wins with a 2-card 6. So a very specialized side bet. It's called the small tiger. And, you know, it's a bet that kind of brings to mind a key card, right? A 6 is an obvious key card, so it may be vulnerable. Now, it turns out I have previously analyzed this side bet with a payout of 22 to 1. And so I contacted the person who sent me this email. "Please verify it's 23 to 1. That may make all the difference in the world as to whether this side bet can be vulnerable or not, right?" So yes, it was verified. This pays 23 to 1. So now let me take you through all of the steps for this one at a time. I mean, this is the process I go through. So step 1, part 1, compute the baseline house edge. All right, how do you do that? Well, I have posted on my website, advancedadvantageplay.com, spreadsheets that actually show you how to do the combinatorial analysis. They're written in VBA, and they'll do it all for you. But in general, what I do is I use a Unix platform, and so this is what it looks like when I'm doing my computations, and I write computer programs. So the program in particular, this one is called baccarat CPP, and let me just show you that program. So here it is. It's just a little C++ computer program. But when you run this program, it actually computes the house edge. Now, let me just take you to the key part of it. It's right here. So essentially what I do is I get the player's total, I get the banker's total, I do a little combinatorial analysis I don't want to get into. And this variable B3 is, does the banker's hand require 3 cards or 2? All right. So what I do then is I say, if the banker beats the player, right, y greater than x, and the banker's total is 6, and the banker doesn't use 3 cards, then that is the event that's going to be winning for us. Otherwise, we're going to tally up a losing event. All right, so that's the basic loop structure that I have here. It runs very, very quickly. Now, after I sort of collect all of the results for all the different ways the game can play out, this is a complete combinatorial analysis, not a simulation. It covers every possible way the game could play out. What I do is I actually print out some data. So I print out the data when the payout is 22 to 1. So here we're paying 22 to 1 on a winner, otherwise you lose 1. And I also print out the data when it pays 23 to 1 on a winning hand. And of course, you lose your unit on a loser. So that's the basic way this thing works. So let me actually run this program for you now so you can see it. So here it is. And I'm just going to run it, and we'll see what it does. So it prints out a bunch of numbers, and in particular, This is the number, if in one complete combinatorial cycle, this is the number of winning hands, this is the number of losing hands. This is the house edge on a 22 to 1 payout. It's 14 point whatever that is, 33%. This is the house edge on a 23 to 1, so it's 10.6%. So you see we have reduced the house edge considerably by going from 22 to 1 to 23 to 1 payout. So that is the first step almost. There's one more part to that. So the other part to that is that I import this data into Excel. So I create these charts right here that identify the winning hand, the number of times that result occurs. I do probability, expected value. So this is sort of a standard methodology for computing house edge when you have a combinatorial result. I'm not going to go through it in great explanation. That's a whole other video to try and explain combinatorial analysis. I just want to show you that I import these numbers, these raw numbers right here are imported into Excel, and they go right into these slots right here and right here. All right, so we have the house edge being computed in these two locations. So, all right, that is step one, right? So what is step two? So step two is to do this thing called computing the effect of removal. So what is the effect of removal? What do I mean by that? Well, what I mean is that we have these cards, ace, 2, 3, and so on, jack, queen, king. And each of them has a certain value for this side bet. We may think that sixes are a great card to have in the shoe and twos are a horrible card, something like that. We don't know, all right? But every card has what's called an effect of removal. And what that number represents is you remove that one card from the 8-deck shoe, right? So 8 decks, that's 416 cards. You take the one card out, an ace, a deuce, whatever it is, that's 415 cards, and you recompute the house edge. Now you put the ace back in, you take the 2 out, and you recompute the house edge. You take the 2 out, put the 2 back in, take a 3 out, compute the house edge, and you do this over and over and over again for each of the cards, ace, 2, 3, up to a king. Now 10, jack, queen, king in baccarat are all the same card. Whereas in blackjack, you have to treat them as separate cards. So there's a little bit of difference in terms of the combinatorial analysis for this. So let me take you once again back to the code that I have here and show you that if you scroll down a little bit, you will see that this essentially is the shoe that I'm working with, right? The shoe has 32 of each of the cards, ace, 2, 3, and so on up to 9, and then it has 128 zero-valued cards. So what I then do, the next step I do in this process, is to change this first 32 to a 31 and rerun the program. I then change that back to a 32 and change this one to a 31 and run the program. I change it back to a 32 and change this to a 31 and run the program. And I keep doing that all the way up till this last one. I change this 128 to 127 and I rerun the program. And for each of those, my program outputs the combinatorial analysis, which will show us the exact house edge for that composition of the shoe, those 415 cards minus the one card we've removed. So I get a different house edge in each of those 10 scenarios, right? I get a different house edge, and I simply am going to put that data into that same Excel spreadsheet. So let's go back to that Excel and let me show you what that looks like. So here is our Excel. And here are the effective removals. So here is the baseline house edge that I computed before, right? That's my baseline house edge with a full shoe. Now, these are all the house edges I get when I remove that particular card. So for example, if I remove an ace, then instead of having a 106079, I have a 106618. If I remove a 6 on the other hand, instead of having this house edge, I'm at 11.25% house edge. So you see taking a single 6 out of that 8-deck shoe has greatly change the edge. And so the effective removals are in this column is simply a subtraction. All I'm doing is taking the new house edge and subtracting that the old house edge from it, right? So this number right here is simply going to be this minus that. This number right here is this minus that. That's how you compute the effect of removal, right? So EOR, effect of removal, very important second step in this. So, all right, what is the next step? Well, the next step is to create a good card counting system, right? We have these effective removals. We want to create a card counting system from them. So let's go back to those effective removals and see how I did that. So here I have in this last column here, the card counting system that I've come up with. All right, now that system, essentially what I'm doing is I'm looking at these effective removals and I'm trying to mirror those in terms of integers. So it's kind of a, I don't know, it's a bit of an art form after a while, but you know what I'm saying is I'm going to treat this number right here as 4, and notice this is positive 0.4, so I chose a 4. This is positive 0.2, so I chose a 2. This is negative 0.6, so I chose a negative 6. These numbers are pretty close to 0, so I chose zeros, right? But you notice that sometimes there's this fudge factor, like I chose a 1 for both 0.078 and a 1 for 1.143, even though it's almost one is almost double the other, right? So there is this fudge in it, but you have to balance the simplicity of the system with sort of the accuracy in trying to match those numbers that you see. And so what I have here is this system and these effective removals, right? So I have these two columns. Now, one of the key things is that this system should be what's known as balanced. In other words, all of those numbers, if you add them up, should add up to 0. So let's just double check that those all add up to 0, right? So we have a balanced card counting system that we've created here. Now the question is, how good is that system? And that's where I use the correlation function in Excel. So essentially it tells me how much these numbers and these numbers sort of match each other if you think in terms of a vector in 13 dimensions or something like that. So you want a number that's as close to 1 as you can get it, but generally if you're over 0.97, you're just fine. So you want to get simplicity in there, but you also need some accuracy, so at least 0.97 for your betting correlation. Anything less than that would be just not work at all. And just to sort of show you, you know, people are so convinced that they should use high-low for everything. So if I were to plug in the high-low system to this, then you notice that I have a 0.0697 correlation. That's horrible, right? So, I mean, people are sort of thinking, oh, can I use the high-low system for this or that or the other thing? And you see that if you do that, you're going to almost be doing exactly the opposite of what you should do for this particular bet. So it's very important to not be attached to some system that you think is just the one you know and therefore it should work for everything. No, high-low does not work for everything. You have a custom system that you're going to be using. The next step is to run a simulation. So let's go back to our programming language here. Let's go back to our Cygwin where we were before. And let me actually show you how we run a simulation now. So let me clear this out. And what we're going to do is go back, and I'm going to go to this other directory. And this is where I run the simulation. Now, the simulation program is actually using a random number generator to play out the game. And this is code that I feel is a little bit proprietary, so I'm not going to exactly share it with you, but I will show you the results of running a simulation. And I'm going to run this for, I don't know, let's run 100 million shoes. Now, this is going to take a while, so I am going to speed this up in post-production, and I will catch you on the other side. Okay, everyone, welcome back. And the program has finished running. And what I want to do is actually tell you just for a second what that data is. So let's go back to that data. And what I'm going to do is sort of scroll up and tell you what I've actually printed out, what the program produced, so that we know what we can do next. So, all right, here is what I have. And if I simply scroll up a little bit, then what this does is it produces CSV output. That's comma separated values, which is something that's particularly easy to import into Excel. So what I have are 3 entries. And the first entry tells me the true count. So the 0 means all true counts of 0 or less. And a 1 would mean a true count between 1 up to 2. 2 would mean 2 up to 3, but not including 3, and so on. I always truncate down on my true counts. So what this says is that in the simulation that I just ran of 100 million shoes, I had this number of hands with a true count of 0 or less. And for those hands, the overall house edge was 14.56%. When the count was between 0 and 1, this is the number of hands I had, and that corresponded to an average house edge of about 9.5%. And so on. You see all of these negative signs correspond to a house edge. But here on 12, when I get to the number 12, we see that we finally have a player edge. It's microscopic at 0.26%, but it is a player edge. And we can see exactly the count. That's going to be my trigger true count. And we can see the number of hands that occurred again at that particular count. So, okay, what I would do in general then is I would just simply copy and paste all of this information into a text file. I would save it as a .csv that I could easily open then in Excel. The next step is going to be to plug the data into Excel. So when I do that, this is what it looks like. I actually then take those pieces of data, and here are those true counts, and here are the number of hands that came up for each true count, and here is the house edge that came up for each true count. And so you see right up to here, this is where we start getting positive values. So, well, the probability is simply going to be this number of hands divided by the total hands played. So how many hands overall were played in this entire simulation? Well, I'm simply going to add up this entire column, and that's what I get right here. This is the total number of hands that were played. If I want to figure out these probabilities, I'm simply dividing this by the total hands played, so I get a probability, and I can get a probability for each true count, and then P times EV gives me the relative weighting of that outcome. I can compute all of those, I add it up, and I get what should correspond pretty closely to the combinatorial house edge. So let's see how our simulation did. Our simulation came up with a house edge of 10.604. Our combinatorial analysis came up with 10.608% house edge. I'd say that's close enough. That's a pretty good simulation that it got that many digits correct. So it takes a little bit of mathematical knowledge to understand this. You need some know about conditional probabilities and conditional expectations and that sort of thing. I'm not going to cover any of that, right? But this spreadsheet kind of lays out exactly what I go through in order to do that. So, all right, there is exactly one more step to this process. This is the final step, is to figure out the card counting stats from this, right? I have this data imported into Excel. Now, what are the card counting stats? And let's just go back and look at that. So all the card counting stats are listed right in this section right here. And can I make this any larger for you? I think I can. Look at that. So with the cut card at 14, we've got a target true count of 12. In each one of these numbers, the hands per shoe with edge, the bet frequency, the average edge, the units won per shoe, and so on, are all a result of the simulation. There's just simple formulas that you can use to come up with these things. I'm not going to go through those formulas, but I'm simply taking the simulation of 100 million shoes, and I'm using that data directly to do this. The desirability index is a little bit more complicated. I have gone through that in another video. But at any rate, these are the final card counting stats for this particular side bet. And you tell me, is this a side bet you would want to play? We're going to win roughly half a unit every 100 hands. We are going to have a bet frequency of about 6% of the hands, 1 out of 16 hands roughly. That does not sound like much fun to me. We're going to get a low win rate. We have a relatively low desirability index. So what I would say is that if you were in a location where this was your only opportunity for an edge, it is an edge, but it's a small one. It is going to be a rare opportunity. And I mean, to me, it doesn't sound like much fun, but at least we did the analysis. So that if somebody said, well, how do you figure out which bets that you want to play? Well, you don't know which ones you want to play until after you've done the analysis, right? So you have to do the analysis. You cannot predict in advance, oh, I definitely know this bet's going to be beatable. You don't know that until you run the analysis. And it takes the full analysis, all of these steps, to verify whether the bet's any good or not. So when someone sends me something, I just don't sort of invent out of the air a count system. I don't invent out of the air the tags or the house edge or how vulnerable it is or whether it's worth attacking or not. It takes this process. Now, I have written enough of these that I can do this essentially in under an hour virtually every time if it's not some super tricky side bet. So this is not hard for me, but for somebody who's doing this the first time, yeah, it takes some groundwork. You need to understand programming. You need to understand how to program baccarat, how to run simulations of baccarat, how to collect the statistics, how to develop the count system, how to plug it into Excel, what are the formulas you use in Excel to get all this other data. I mean, it's a lot, right? I agree, it is a lot. But it is certainly something that someone who is invested in beating casino games, who has the skills of understanding probability theory, of knowing how to program, and knowing the particular game they want to play, who has sort of the ability to transfer that game into code, it is definitely something that you could do for yourself. You don't need me to be doing this. So I hope this helps you. All 40 people out there who think that they can now beat casino games on their own by writing their own code, good for you. Go do it, all right? I'm 100% behind you. For the rest of you, it's been an adventure, so I hope you've stayed with me and you've enjoyed this video. So, all right, everyone, this is Elliot Jacobson. See you later.